Greetings from IIT Kanpur. So, we continue our discussion on diffusion. We go a little deeper this time as much as this introductory course will allow. So, today we discuss about diffusion part 3. The disclaimer. So, just to review what all we looked at, in part 1 we got the general introduction. Part 2 we got deeper into what may be needed in VLSI, and part 3 we look at some special topics as much might be reasonable for this introductory part. So, this is what we will discuss today. It has 3 sections. So, let us get started. First, I want to talk to you about the concept of thermal budget. I am taking my inspiration from what I learned from Sir Nathan Chung, and let me see whether I can convey what he used to so elegantly convey in the next slide. So, thermal budget. If you look at it, diffusion constant is independent, if you consider it to be independent of the doping concentration, hence over X. Okay. So, first order we are making that assumption, although of course, this may not be true, as we will see in some of the later parts of this talk itself. So, but then the temperature, even if the diffusion constant is constant with respect to X, it may vary with time. Why would this happen? One practical reason may be you may have one process, part of a process going at a particular temperature, then it will go to a slightly higher temperature for another duration of time, and then you will come back to another temperature and so on. So, the temperature may vary with time, and so diffusion constant strictly is a function of time. Okay. Although you may have a process where you are keeping the temperature constant, and so it is diffusion constant is constant with respect to time as well, but in a full process you will have phases where it may go to another temperature, that means diffusion constant has changed. But first order we are assuming, at least for the initial discussion, that diffusion constant does not change with position. So, this is the equation that we have seen that came out because diffusion constant was independent of position, and that is why it came out of the second time we were differentiating it, and we got this relationship, which is the popular canonical form. Now, let me define a variable beta, which we can say is the integral of diffusion constant over time, because what I mentioned just now, I am assuming that d need not be constant with time. So, if that is the case, we can define a variable beta is equal to integral 0 to t d of t dt. Okay. So, therefore, it is immediately evident, if you take the derivative on both sides with respect to t, you will find that d of t is equal to delta beta by delta t. So, then we can go back to our relationship, the first equation, and we could do some mathematical jugglery. The left hand side we can write delta c over delta beta times delta beta delta t. Okay. And the right hand side, which is d of t, we see that from number 3 that it is delta beta delta t and times delta second derivative of c with respect to x. Or this equation 4 simplifies to the derivative of c with respect to beta, it is a new variable, beta is equal to delta c delta 2c delta x square. Okay. So, now this is a relationship that we have, this is a modified form, 5 is a modified form of equation 1. But supposing temperature was constant, then d was also constant, is time independent. So, equation 1 could directly also be looked at in this form in equation 6, that is, you can bring the d of t, which is not a function of t now, it is just d on the left hand side, and so you will find you can write it as delta c delta of dt is equal to delta 2c delta x square. So, this is an interesting thing. So, when we compare equation 6 and equation 5, what we find is the beta which we derived from calculus, the delta C delta beta is equal to delta 2 C delta x square, but if it's a constant, it is just dt. So that brings to mind, can we somehow define an equivalent constant d or something, or constant dt rather, so which will end up or not constant dt but equivalent dt we can actually define, and then we can actually look at the whole thing in a slightly different perspective. So comparing 5 and 6, one finds that replacing dt product in the diffusion equation beta will satisfy the time dependent diffusion equation. Okay, so then can this beta be defined in a particular way such that there is an equivalence? So let us look at it. If a series of n diffusion cycles are considered, okay, for temperature T1 and time T1, and then we go to another diffusion cycle, time T2, temperature T2, time T2, then we go to and so on up to Tn, temperature Tn, time Tn. So there are multiple cycles and each of them will have their own value of d, correct? So within this cycle, Ti's are constant and hence d's within that cycle is constant. So within that cycle you have a dt defined. So beta can be defined, and actually it comes directly from the definition of equation 2 itself. Beta is equal to d1 t1 plus d2 t2 and so on dn tn. Okay, so that is, it's a summation of all the dt that is there for the different processes. Could we define this as effective dt? And actually it is not a bad idea, as we will see. The beta is the sum of d times t, this sum of the dt products, and this actually sort of defines how much variation is happening during the whole process, how much of the straggle is increasing, how much of the variance is increasing. It's sort of a measure. So this sometimes the beta, which is the sum of all the dt products, okay, d times t product, sum of all of that for the various individual process steps that are involved, that is sometimes called the thermal budget. So you can actually say that how much is the maximum dt that we are allowed for a particular device profile. Okay, if you go for more than that, there will be repercussions in terms of how much the variance will change. So let's go forward and see about it. So thermal budget tells the extent of dopant redistribution during the thermal cycle. Okay, and we have already seen that dt is actually nothing but is proportional to the variance. 2 dt was actually the variance that we had in the distribution, in the concentration, because of that particular process. So as IC fabrication proceeds, thermal budget of later processes need to be small, because if they are big, you will have everything smeared out. Say you put a very narrow distribution of dopant somewhere, and then you come to the next cycle where the dt values are large. Why can it be large? Either because you went to high temperatures, or you annealed for a long time, or the thermal process was for a long time. So the dt value for that was large. So it ends up becoming such that you use up all the thermal budget in that particular process, or even may exceed it. If you exceed it, your devices are not guaranteed to work. So as IC fabrication processes proceeds, we need to make sure that the thermal budget of the later processes are as small as possible. So all the high temperature and longer time process usually is in the beginning, and all the lower temperature and low time processes you try to push it towards the end. And if you have some processing in the end, try to make sure as small thermal budget is possible in that. For small dimensions, smaller thermal budgets are desired. Why? Because dt is 2 dt is essentially the variance that is added by a particular process. If that is the case, you are ending up smearing it much more. So small devices, you don't want to smear things much, right? So that being the case, you will have to make sure small dimensions, you keep the thermal budget of your whole processes as low as possible. In fact, if you notice, the temperatures earlier were often 1000 degrees, 900 degrees for various silicon processes. Today, as the dimensions have shrunk, the temperatures have come down to 900, and that makes sense, because you want to keep the thermal budget low. And lower temperature, remember D is actually exponentially dependent on temperature, right? So higher the temperature, much higher will be D. So when you go from 1000 to 900, you get a reduction in the thermal budget of the process that will happen. Of course, time is also a factor, but time is linear. So that way it is little bit more accommodating than temperature. If you go even with 10 degrees, exponentially it is going to increase the value of D. So your thermal budget will end up becoming exhausted. Additional variance in concentration profile is due to the thermal process, and it is given by 2 dt, which I mentioned. So typically any process that you have, and which we already saw earlier when we were looking at the complementary error function, what was the extent of the standard deviation, that was square root of 2 dt, right? So, so 2 dt is the variance, square of the standard deviation. So that is why you want to keep the overall dt, equivalent dt as we saw, or the beta, to be as small as possible for the full process. Alternatively, you decide how much is the maximum variance you can allow, and then budget the different processes accordingly. And if you find that some process is very high temperature, you have to find alternatives of getting it done at a lower temperature by other means, maybe plasma processing or high pressure oxidation, and so on, that we looked at. So that brings down the temperature, and that means the thermal budget is available. Thus, thermal budget summation of I to n, I equal to 1 to n di times Ti is proportional to the variance added to the concentration profile, and this is a very important concept that we should keep in mind when we are dealing with the diffusion process. The thermal budget that is available, and the diffusion process, as we have already seen, is conscious, and sometimes it is there because we are doing some other process. Supposing you are doing oxidation, or you are doing some other diffusion. So the earlier diffusion is also going through the thermal cycles. So you have to budget all that variance addition that is going to happen, and a good way of doing that would be to keep track of d times t for each process, such that the total the dt products of all the different processes are within the value that is acceptable to you, so that the profiles do not get smeared out. So you have to, so the key takeaways, later cycle processes should be as lower thermal budget as possible, so that earlier processes are affected the least. Smaller devices, go for smaller thermal budget, because you do not want too much smearing out. That means the smaller devices will all be smeared out, and you will not be able to define it very precisely. And you have to keep track of all the thermal budgets that come up because of all the thermal processes that happens in your devices. The good news is, when we come back to room temperature, the thermal budgets come down for many of these diffusion processes, because it is exponentially dependent. So when you come from 800 degrees to say 25 degrees or 30 degrees, the diffusion d value is so small, say you can ignore that for practical purposes. So even if you are using the device for 10 years, the dt of that, when the device is being used, the thermal budget component that is there when you are using the device is negligible, and that is why we are able to use them. Okay, I will now go to the next point of discussion. We looked at the important concept of thermal budget, which required a knowledge of the diffusion constant for a particular process. But then this diffusion constant which we looked at a canonical form, right, standard form, which told us what the d is likely to be, and we saw a simple way of deriving it. But the reality is, as always, much more complex than the way we try to start understanding it. So here I will be talking a little bit, give you a glimpse of the diffusion mechanisms that are there. And strictly speaking, one should be always on the lookout for all types of different diffusion mechanisms and keep track of them. So let us get started. So this is on diffusion mechanisms. Any of the textbooks that are discussed are a good read. Gandhi's book has a lot of details on this diffusion. He has covered it very well. Wolfentauber has also covered some of the key aspects of it well, and so has Professor Z in his book. So what is the outline? The broad outline is actually quite simple. I want to tell you some examples of the diffusion mechanism. Please note, this is not exhaustive, but these are some of the key diffusion mechanisms you encounter. So I will talk of the examples of diffusion mechanism, and then I will talk of the components in diffusion mechanism, which actually the final diffusion constant is actually a combination of many diffusion constants. So, I will try to say what are the components in it and how they get affected, and sometimes some other factors like the background concentration and other things can also play a very important role. So, this is just a sample I have taken from the textbooks. Many of the textbooks show this. So, one of the ways in which something can diffuse, let us assume that the black dot is what is the impurity or the dopant that is being tracked, and we want to know how it diffuses, and it is going from left to right, say. Okay. So, supposing there is it is a locational lattice impurity or lattice sitting at the lattice point. How will it move to the right? It can have an exchange. The dopant can go to the point of where the semiconductor is, say silicon here, and the silicon can go exchange its position with that and come here. So, the black dot has moved to the right. So, it starts moving from left to right. This is known as the exchange mechanism. Now, how probable is this? What is the chance of it happening? In what crystal? These all have to be evaluated for that particular crystal and for the particular scenario, temperature and so on. You can actually try to do experiments to find out what is this type of phenomena, and actually sometimes it is all mixed with many other information, but you have to design experiments so that you are able to distill it out. So, you can find out what the exchange rate is. So, now once it has exchanged this way, it can again exchange this way and so on. And as we saw, the diffusion is happening because it can move both directions, but where the concentration is more of them are going to the direction where less are present, and where the concentration is less number are actually coming to the regions which are higher concentration. So, eventually there is a diffusion trend that we see. So, another mechanism can be diffusion from vacancy locations. So, there could be a silicon matrix, for example, where vacancies could be formed because of some earlier processes. Say there is an ion implantation, and because of the ion implantation, silicon atoms are moved away from their lattice locations and vacancies are created there. If that is the case, once in a while you will find vacancy in the matrix, but there could be dopants that are already present a priori before the implantation or just earlier implantation. Okay. So, those impurities could also switch to the vacancy. Some of the diffusion actually takes place this way. Actually, it depends on the atom and the conditions. According to that, one of these methods will be preferred. So, vacancy mechanism will happen. Again, you will have to derive the diffusion constant corresponding to this vacancy. So, for this vacancy diffusion mechanism, what is the probability of finding a vacancy, and what is the probability of it hopping to the vacancy site, and what is the probability that it will not hop back, because one is leaving a site, there is another site. So, all these can be evaluated or have to be studied, okay, and modeled, and then you get a diffusion constant corresponding to vacancy diffusion. Another interesting thing is interstitial C. Okay. So, what it means is, supposing you have a silicon matrix and there are a whole bunch of interstitials that are present. Here I am representing by one self-interstitial, that is the interstitial which corresponds to the main atomic matrix in which you are studying. So, silicon matrix, this could be a silicon interstitial, and then there will be a, supposing this is a dopant atom. So, in interstitial C, when there is a sea of in the sea of silicon, once in a while you find some interstitial. What is chance that this interstitial will end up pushing out this atom and sitting in the interstitial by itself? As you would imagine, if you had a bulky atom, the chances are that this silicon atom the matrix would prefer silicon to sit there than the bulky atom, or maybe a very small atom. So, based on these you will have to calculate, because the best fit in a silicon crystal would be silicon atom itself, right? Any other atom, there is a small mismatch. So, these values, these things have been calculated, and those mismatches of course depend on the environment and the conditions under which you are studying them. So, interstitial C essentially means if you have a system where there are lots of interstitials and the dopants are sitting in the lattice locations, what is the probability or what is the rate at which the the dopant atom will be kicked out of the lattice location, and the interstitial will go and sit in its location. Once it has come here, you will find that another diffusion mechanism will take over. That is, the dopant is an interstitial now, how it will move out. But when you have a matrix where there are lots of dopants already sitting there and interstitials are appearing in the scene, what is the chance that the interstitials of the original atom will end up replacing the dopant atom and sit in the lattice location? So that is interstitial C, and this is a very important method by which diffusion happens in many of them, especially phosphorus. You find that this plays a very important role. Now, another method of diffusion is interstitial diffusion. Here, of course, say you have implanted some atom and it is sitting in the interstitial location, or due to interstitial C, the atom has gone to an interstitial location. Now, what is the rate of this interstitial going from one interstitial to another interstitial to another interstitial, and then it can go deep, right? And then, of course, at some point there could be a vacancy where it can sit in that, or some of the other things can happen. Then there is something called a Frank-Turnbull. So it can keep going until it finds a vacancy. Once it finds a vacancy, the interstitial will jump and sit into that location. Okay, so this is the Frank-Turnbull model. It turns out that each of this play a very important role under certain conditions and certain locations in the wafer where the diffusion is taking place. Okay, so then you have finally, there are many others. I shouldn't say finally, there are many others. So there is also the kick-out mechanism. That is, it's almost similar, in a way opposite to what interstitial C is. Here you have the original the dopant atom, which is interstitial. It comes and kicks out the silicon atom, the host atom, from its lattice site and then takes its place. Okay, so once it does that, of course it starts then contributing for its dopant value. For example, an acceptor will end up giving holes, and donors will end up giving electrons for the system, right, making it p-type and n-type respectively. So this kick out is another mechanism. So what I want to impress upon you is there are a range of ways in which this diffusion happens. This is just a glimpse, and people are continuing to look at other ways and to explain, and sometimes they look very complicated, but it ends up that that's what seems to explain the situation better. So you may have to rely on such things. So you have to find out what are the different methods, and for each of the method, it will be a good idea to find out what is the diffusion constant corresponding to that, and you give weightage to what the overall way in which diffusion is taking place. Often you give it equal weightage, but then sometimes you weight it by the number of other species that are present. Okay, so let us see how that can be done. So this is another picture which shows how the vacancies, point defect configurations could be. This is a case. So this is a case where there is a vacancy. Okay, but it turns out this vacancy is positive charge. It results in a net positive charge. You could also have vacancy which is neutral. There is something vacant, but it's neutral. You don't realize electrically that there is a vacancy. But then you can also have vacancies where it ends up that the neighboring atoms interact, and then you end up having some extra position which ends up filled with an electron that is roaming around. So you can have a negative vacancy which can be negative. Now this plays a very important role, because depending on how many electrons or holes that are floating around in the system, accordingly those point defects will play an important role in the diffusion mechanism. You could have also some others. You could have a tetrahedral interstitial where the interstitial ends up interacting with 4 other atoms. You could have a hexagonal interstitial where the interstitial which is sitting in the lattice is ending up interacting with 6. The examples given here are for the diamond-like lattice, silicon lattice essentially. So you can see that these interstitials are coming and sitting where it should not be sitting, right? Similarly, you can have acceptor interstitial which can be neutral, and acceptor interstitial could also be positive or negative. Okay, acceptor atom could go into the location, and then it ends up acceptor interstitial can end up being neutral, although it's an acceptor atom, but it's neutral, somehow it is very stable. Then you could also have it positive or negative. Okay. So now we saw that there are various mechanisms of having diffusion. We also saw a little glimpse of what these interstitials could be, vacancy as well as interstitials, as well as some neutral species which could be there, which could be charged also. So let's see how the diffusion constant can be determined in a practical situation. So what we do is we make an assumption here, as we normally do in most of the work that we deal with in engineering and technology. We linearize it, and we also assume that each process is orthogonal to the other. That is, one process is not going to affect the next process. First order, you assume that. Once you assume that, you often find that it doesn't fit exactly, or there can be some error. It explains but not explains fully. Then you come in and bring in the interaction term as another process or something like that. That's how the way it goes. So what you do is, the diffusion constant for a particular diffusion, you will say that it is equal to d1 plus d2 plus d3 plus so on. In theory, as many processes there are, but in reality you take only the processes which dominate, which are very rare. You don't want to, it will be in the 6th decimal place or something. You don't have to worry about it, right? So you assume the dominant diffusion process, and you the d would be equal to d1 plus d2 plus d3. So it's linearized. Okay. So most diffusion depends on substitutional diffusion, impurities, interstitials, and vacancy. These are some of the popular ones that we look at. And each mode of diffusion has its own diffusion constant, having its own prefactor and energy barrier. So each of this d would have a prefactor. So d01, d02, d03. Each of them will have an energy barrier. Some may have such very high energy barriers, so they rarely happen. Some have very low energy barriers, so as soon as it's available, it happens, right? So such things can happen. So this is how first order you model it. But then you want to also sometimes give emphasis to what is in the environment. So there could be a charge state which is aiding in diffusion, but the charge state will aid in diffusion only if carriers are present, so as to ensure charge neutrality is ensured, right? So for example, if d equal to some d0 plus d1 minus, if it is d1 minus, obviously it will facilitate in diffusion if there are lots of electrons. Okay. So it will be weighed by this component is going to be, it's a weighted sum now. Earlier it was just a sum. We are saying we will go for a weighted sum, some d0 which is independent of n, and some d1 minus where the diffusion mechanism is aided by the presence of electrons. And so it will be multiplied by the number of electrons present with respect to the intrinsic value, because intrinsic value always is present. Okay. So but then when you take n type, how much more is it from the intrinsic? So it will be multiplied by d1 minus into n by ni. Similarly, of course, once you can say negative, you can also talk of positives, right? So supposing there is a position which is affected by the presence of holes, it's a positive thing. So presence of holes means it will affect it in a particular way, because if there are lots of holes, the positive will not want to be there, right? It will want to go away. So d is equal to d0 plus d1 plus by p divided by ni. So you see the difference here, it's weighted by n, here it's weighted by p, that is electrons and holes. Accordingly, it will be weighted. So this is one way in which you can model the things. So supposing some defect states have multiple charges. So we saw defect state is one charge, right? So far. Supposing it has two charges, because of the way it is located, there are absence of two electrons, or two additional electrons are coming and sitting and hanging around there. Now, if there are more electrons present there, if the concentration of electron goes up, so that diffusion mechanism will be facilitated much more, because the negative charge will want to go away, right? So you will find that d equal to d at 0 neutral charge, dx, the x process with one charge, two charges, three charges. and similarly you can have negative also, I have not indicated here. So, D is equal to, you can write that as what is shown here. So, essentially all the negative, single and negative charge that are present will be weighted by n by ni. If 2 are present, it will be weighted by n square by ni square, 3 are present, n cube by ni cube. Now, it turns out in the following way, usually higher charge defects are unlikely to be there, but if the doping concentration is very high, then their effect shows up very much, because they will be the first, because of the n cubed by ni cube, for example, supposing plus 3 minus 3 charge is there. So, n cubed by ni cube factor will end up make this dominant when the doping concentration is high. In the regions where doping concentration is high, they will end up doping this. Why is this? So, maybe we can take a quick look at the law of mass action. So, law of mass action you must have all studied in your physics, chemistry. So, essentially for a reaction, small a times capital A plus small b times capital B will give you, say, C times capital C. So, the reaction rate can be indicated by concentration of A to the power A, concentration of B to the power B, and concentration to C, it will be Kc. Well, and how is Kc defined? Kc will have a prefactor multiplied by the Gibbs free energy change because of the reaction going from one left side to right side, that probability you can multiply. So, this will be the rate reaction. So, we will just invoke this in the context of our vacancy, for example, playing a role with electrons, or it could be with holes, I am showing with electrons here. So, say V equal to, say, some vacancy plus Re will give you Vr minus. Okay. So, clearly based on law of mass action, we can see Kc would be the rate at which the reaction would take place or the process will take place will be the vacancy concentration times n to the power R divided by Vr minus, and in this case it will be Ni and divided by R minus, intrinsic R minus. So, what is intrinsically present versus what is present in the particular case. Therefore, the V of R minus divided by V intrinsic R minus, how much intrinsically such things will be present, would be n by Ni whole to the power R. So, eventually note that the vacancies which are higher states will have to go to a level where what is intrinsically present in the background. If they are present more than what is intrinsic, that is when the effect will be pronounced. That is what this is also trying to indicate. So, here you have, so based on this you can see that D is equal to indicated these various individual diffusion constants corresponding to the vacancy state or the interstitial state with the appropriate charge that is there, and that is weighed by the background doping. So, what is this indicating? Our assumption that diffusion constant is independent of position is turned on its head if we just assume the single diffusion constant. Why? Obviously, there is difference of doping at various places. So, that means because of the higher doping, some other phenomena is going to bring in. How do you tackle it? We do not let go of our canonical form, but we invoke a new diffusion process which involves that particular species and include that, and eventually we talk of the overall diffusion constant to be equal to weighted sum of the individual diffusion constant, and that is in a way the effective diffusion constant. This is the way we model the diffusion process. So, what are the key takeaways? There are little conceptual points I want you to think about these, and I am sure when you think about it, maybe you will have a better way of understanding it and realizing what is happening. So, let us see, diffusion happens by various mechanisms. Okay. The overall diffusion coefficient is the sum of the diffusion coefficients of all different processes. Of course, it assumes that these are orthogonal processes and independent processes, and they do not affect each other. One happening does not affect the other, right? That is the assumption. So, this we are linearizing and we are assuming this because it is easier to get a quick grip on what is happening. Creation of interstitials and vacancies due to other processes can also affect the doping profile. Okay. So, that is a reality, and diffusion coefficient depends on charge states that get modified with the doping, right. And higher the charge state, more the dependence on carrier densities that are available, and doping concentration can affect these components of diffusion process. Okay, so this is essentially a nutshell a good way of tackling this complex issue by linearizing it and assuming orthogonal processes to the extent possible, and then you are able to talk of an effective diffusion constant. Okay, now we come to the last part of this particular lecture. Here we talk about some of the offbeat factors away from the canonical form of diffusion that we first talked about in the first two lectures of diffusion. So let's see what are the ways in which we find this deviation, and one of the ways to tackle this deviation, of course, is by the immediately discussed slides on how to model the diffusion constant. So let's take a peek at some of the examples that people came up and how they ended up solving. No way is it exhaustive, and in fact there are many other ways in which these things play a role, and a lot of studies have been done in this, and a lot of literature is available, and I welcome you to explore this because it's a fascinating field where you can see how it deviates from the normal, and how by clear understanding and analysis you can delineate it and understand what is happening and come up with a way to model that. Here too I will encourage you to look at the standard textbooks, especially Gandhi's book has gone in some detail on some of these with references, and also they talk about gallium arsenide as well. I have mainly stuck to silicon discussions. So this is what I plan to cover. As I said, no way exhaustive, but just giving you a glimpse of what is there. Effect of built-in electric field that happens as you are diffusing dopants. See, dopants by their very nature are going to come into the silicon matrix and release some electrons or holes. So that means there are going to be some charge states that are available. That means electric field comes in. How does it affect our diffusion? So a quick peek in that. It's fascinating that it plays a very critical role, especially in silicon and in all the semiconductors, where they go and substitute the original host atom and then become active electrically. So then they play a role. And a few other quick things I would like to show how they found that when you are doping phosphorus, you have a model and you are able to explain something, but somehow towards the end the tail is somehow elongated. How do you explain that? So let's take a look at how they have explained it. Then something called the emitter push effect. This is more of a BJT phenomena, bipolar junction transistor phenomena. That being said, it's good to know about these because you never know in what context it is going to pop up, even when you are going to deal with other devices, right? But the emitter push effect initially puzzled people. They are making transistors, they are based on the calculations of diffusion and all, gate width should be something, but they found that the gate width, the overall performance is poor, indicative of a larger gate width. So how do you explain that? Then a couple of them related to oxidation. In the context of oxidation, there is a curious case of oxygen enhanced and reduced diffusion, which we will see, and how they tackled it. I'll just of course show the results and show what they finally found out. But when it was originally there, it was like a mystery problem, and you had to go systematically and analyze it, and finally when you solve it, of course it's obvious, right? Finally, dopant redistribution during oxidation of silicon. This is important because often you end up oxidizing silicon, or it happens that silicon oxidizes, and so near that the dopants will get distributed. So you have to know how it happens. A snapshot, something to keep in mind. Of course, modeling tools are very well developed now, and they often incorporate this. If not, you can at least use a rule of thumb and get an estimate. So let's get started. First, we'll talk of electric field enhanced diffusion. I have two slides on this, so I'm calling it 1 and 2. So the first I would like to tell what I am trying to tell here. Supposing you are doing diffusion of some dopants, and the profile that you are having at any instant of time is as is shown. Now, very often at these high temperatures and so on, you'll find that they are likely to sit in substitutional sites, and they are likely to ionize and contribute to the carriers that are needed for that particular for system, right? For that energy level that they have, they say you can create electrons or you can create holes. So that means the number of electrons and holes created will be almost identical to what you have in terms of the dopants. So strictly they should be identical, right? But that being said, because it's at temperatures higher than 0, the dopants of course are diffusing, so are the carriers. Electrons are also diffusing, holes are also diffusing. Remember that holes and electrons are very light, so they will diffuse much faster than the dopants. Okay, so what does it mean? There are a lot of electrons sitting here. Obviously they will diffuse faster than the ions, but then as soon as they start diffusing, some issues come up. You will find that the center of gravity of the electrons is shifting from left to the right. When the electrons are shifting, what happens to the dopants? They are also charged ions now, because they have released the electrons and they have created the electrons in the first place. So the ions or the positive charge is to the left. Yes, the dopants are diffusing, but they are diffusing much slowly compared to this. So what ends up happening is the electron tries to run away, but the positive ions, if I am talking of donors for example, positive ions are pulling it back. If I am talking of the acceptors, the holes are trying to pull away, but the negative ions will pull back the holes. So what ends up happening is an electric field is actually created, which holds back the electrons and holes depending on the dopants. On the other hand, the electric field will also push the positive ions and the negative ions that are there, right, depending on what the direction of field is, right. So what I am trying to tell is, if you take donors, electrons are formed, it's trying to move away, and the positive donor atoms are pulling it back, but there is an electric field that is created. Now it turns out that while often we assume that the number of donors is equal to number of electrons, and which is a good assumption for most cases where the doping concentration changes slowly, but usually you will have some difference in the two. The extent of difference usually is of the order of the Debye length. Okay, but first order you can assume that they are almost coincidental, and what I am showing you is exaggerated. They certainly won't be so much far apart, they will be slightly far apart, enough to create the electric field which is pulling back the thing. You must have come across such concepts when you are studying the p-n junction, right, especially the how diffusion and drift balance each other. So let us quickly see how to model this mathematically. Dopants coming into the semiconductor ionize, releasing free carriers, and that is assuming that they are substitutional diffusion. The ions are, as well as the carriers, diffuse through the semiconductor. Okay, both of them are diffusing because there is a difference in the concentration gradients. Acceptors form negative ions and holes, while donors form positive ions and electrons. So let us consider the dopants case. You can argue for both, but for simplicity let us consider that the dopants are donors and the carriers will be electrons. So higher diffusivity electrons will try to pull away from lower diffusivity donor ions, but charge separation causes an electric field which holds the electron back. But what is more important for us in this context of diffusion is the electric field will also try to pull the donor ions faster than the way it is diffusing. So that is actually ending up making the diffusion faster. So this inbuilt electric field effect actually gives you higher diffusion than what you would expect if they were not charged. So let us continue our analysis and let us look at it mathematically. This is the same diagram which I had in the previous slide. So since dopants are ionized, they drift as well as diffuse. So since they are ionized and there is an inbuilt electric field created we are talking about, let us assume that it is some E, and then the flux of donor would be JD is equal to minus D delta ND delta X. This is just the flux of thing. I am not talking of electric current or anything, just the flux. That is why I have not multiplied by the charge. So D is equal to delta ND delta X, that is the concentration gradient of the donor ions, plus another term I am adding, the mobility times the electric field times the concentration of the dopant ions. Here of course I am assuming they are 100% ionized, which is the case except when you go for very high doping levels or when you are going to low temperatures. But since doping is happening at high temperatures, they are likely to be ionized. So the flux of electron also that are there will be like this. So Jn is equal to minus Dn delta n delta x. The Dn is the diffusion constant for electrons as they diffuse in the material, times the profile of the profile gradient of the electron minus mu n electric field times n. Now, negative sign I have had in the second one is because they actually will move in the opposite direction to the electric field, correct. So, I have indicated that with a minus sign, and this is the actual number of how the electrons are going to go. But we know that electron current has to be 0 because there is no bias applied, and thermodynamically you cannot just create energy, right. So, even you have to assume that the current, what assume, it will be that electron current is 0, right. If electron current is 0, the equation 2 you can actually make it equal to right hand side is equal to 0, left hand side is that is the whole thing is equal to 0, left hand side and right hand side both are equal to 0, and then you invoke the famous Einstein's equation, Einstein's relation. So, you have di, the diffusion constant is equal to kT over q times the mobility. This is true for any species, okay. We can use it for electron, we can use it for holes, we can use it for ions, anything that we can assume that this is the case when it is close to thermal equilibrium situations. So, electric field equation 2 will then boil down to minus dn by mu n plus 1 over n delta n by delta x. This, using the Einstein's relationship, will become minus kT over q 1 over n delta n delta x. So, we have now found what is the electric field that is actually created in terms of the concentration of electrons and the concentration gradient that we have in a way, and it is proportional to the thermal voltage, and that as we can see. So, now from 1 and 4, actually this electric field I have got, so I will plug it into the relationship I have for the donor ions. So, JD is equal to minus D, it is just about by manipulation you will find, and plugging this E value there and then taking out things common out, and of course again invoking the Einstein's relationship, this time for the ions, that is D ion and mu ion, right. You end up getting that JD is equal to D 1 plus ND by N delta N by N times the slope and the concentration. What do you notice? Originally we thought it was D times this, but we are having a factor which ends up becoming it seems to be adding something to it. So, comparing 5 with the canonical form, we can talk of D effective, which will be D times the term in the bracket, which is the ratio of the concentration of the donor ion and the electron, and the way in which the difference in the change that we notice in the two, ratio of that. So, we can define D effective to be equal to D effective times H. So, H is called the diffusion enhancement factor, which is now defined this is for convenience. So, essentially you have a standard model, instead of trying to derive everything from the beginning, you say that there is an enhancement factor and you use the same diffusion equations, and all the things that you have derived you can actually immediately start using, but with a new diffusion constant which is D effective, and D effective is equal to D times enhancement factor. Enhancement factor is as is given. So, this is what you have. So, invoking charge neutrality, now this is something it's a way of expressing and conveniently, and I will welcome you to work it out as an exercise, those who are familiar in semiconductor devices. Now, you can invoke charge neutrality and 100% ionization of the donor atoms in thermal equilibrium or close to thermal equilibrium conditions. You have the negative, the positive charges, that is ions, assuming 100% ionization, and holes is equal to N. But we also know that at thermal equilibrium or quasi thermal equilibrium, we are assuming that is holding or close to holding, Ni square is equal to N times P. So, then you will end up, you replace this in the left hand side equation, this equation, and then you will find that you get a quadratic term, and you can actually manipulate it. You can try to do the derivatives of these, and you can end up finding what H is. And this, as we can see from, I will welcome you to work it out. It's an interesting exercise. You will find that the enhancement factor will be Nd divided by 2 Ni divided by 1 plus Nd by 2 Ni. Okay. So, and the denominator to the power half, right. So, essentially it's 1 over square root of 1 plus Nd by 2 Ni, Nd Ni whole square. Okay. So, now it turns, so essentially this is something for modeling it more accurately, and you're welcome to do that. But the point I want to make is the enhancement factor can be of the order of, it will be more than 1, right? It will not be, so essentially D effective will be greater than D. That's what we find. And that's very interesting. So what it means is the diffusion by the thermal process is making it diffuse in a particular way. But because of the creation of electrons and the electrons pulling it, that also adds to the diffusion. So electrostatic process actually ends up enhancing the diffusion, and this is something that you have to keep in mind. And this is one of the things they had to worry about, because many times they wanted to control it. They found that diffusion was happening more than what it should. So with these understandings, they are able to model it more accurately. Let us now look at some other anomalous behaviors that we have come across. So diffusion in the tail of phosphorus the concentration. So supposing you are diffusing phosphorus, and usually the solid solubility is pretty high, and you find that here the ionization will be a little less, because you remember that the Boltzmann, you have to go to the rigorous Fermi-Dirac statistics to find out how much is ionized. So but anyway, it's significantly high, it's well above 10 to the power 20. So at the surface, as it is diffusing, you have a very high concentration of phosphorus. But as you go down, what you find is it falls precipitously. This is because of what affects the diffusion of that. So that is not available as much, so it falls precipitously. But then you find there is a kink, and for the lower doped phosphorus, these regions are less doped with phosphorus, they seem to diffuse faster. So you find a kink here, and the tail is actually slightly longer. So this problem, actually in Gandhi's book, he has referred to that paper, we quoted that paper. As you can see, the diffusion at the tail, the diffusion constant of the tail, if you calculate and based on the profiles you are getting, at 900 degrees centigrade, when the surface concentration is 10 to the power 18, 10 to the power 19 and all, it doesn't change much. But when it goes to 10 to the power, little above 10 to the power 19, even at 900 degrees centigrade, you find that the tail diffusion actually starts to become faster than what it was. This is not very easy to explain, right? Similarly, 1100, of course, 1100 everything is fast, but above 10 to the power 20, you find that the tail seems to diffuse faster. So when you go for very high doping, the tail seems to have a kink. How can you explain this? So just some background, phosphorus solid solubility is 10 to the power 21, as I said, very high, almost 1 in 100, so a few hundreds is actually is phosphorus when it is doped at that level, is dissolved at that level. The carrier contribution ends up becoming slightly less, 10 to the power 3 times 10 to the power 20. Okay, that's a maximum, typically high value you can get. Now diffusion, what is happening? Diffusion strongly affected by neutrals and charge vacancies. That's the reality. It's not a simple diffusion. There are actually interstitials, neutrals and other things, and vacancies all are playing a role. So it seems that neutral and charged vacancies play an important role. So when phosphorus diffuses, lot of vacancies are there, and interstitials are also created here. So now that being said, phosphorus also diffuses by interstitial C. So essentially the interstitial silicon atom comes and kicks out the phosphorus, and that allows it to diffuse further and further. Okay, so both play a role. So what is happening? At the surface, you have a super saturation of self interstitials because of the silicon that is displaced as phosphorus is coming in and sitting in its position. So you will have a super saturation of self interstitials. So interstitial C plays a role, but it is sort of saturated, it is not showing up. And the P vacancy that you have, the P vacancy interaction controls the diffusion, with the acceptor vacancy of charge -2 playing a very important role. So that ends up dominating the diffusion for the very high doping region. On the other hand, the interstitials that are formed here, the self interstitials are also diffusing inside. As they are diffusing inside, they end up increasing the diffusion rate here because of interstitial C, and that means that the tail is disproportionately diffusing more. So suddenly you find some other phenomena is also dominating in the low doped regions of the profile. So this sort of explains it. That being said, of course, there are lots of discussions and lots of theories, and people are trying to explain it in various ways. This seems to sort of explain what was happening. And because why is this important? It tells you where the junctions will be formed, where the neighboring devices, how they are going to be affected. So it's important to understand these. Let's now look at the very interesting thing, emitter push effect. So this is shown schematically here. This picture I have taken from Gandhi. It's also available in other textbooks as well. So when you have, say, a collector region, a base region, and an emitter region. Now when you do the diffusions, you expect something like this. But what you end up getting is something like this. You find that the regions that is directly under the emitter, you find that it has moved further away by a delta. But these regions have not. It's a very funny thing. So this puzzled people, and what does it mean? The base width is actually equal difference between the emitter base junction and the base collector junction. So you see that is actually enhanced by a factor of by amount delta. So when it is enhanced by amount delta, that means that the transistor gain is going to drop. So with heavily doped emitter, base collector junction pushes out, okay, and BJT gain decreases as base width increases. So this, whatever they are trying, they are finding the transistor gain is not going up. Why is it? And when you do the profile, you are getting something like this. But your diffusion relationship and all says that this should not happen. So what was happening? So electric field, they tried to use it, but electric field strictly should have worked the other way. Because remember that, say, let's assume that we have an N plus Pn transistor. So phosphorus is being diffused here. So the electric field is actually trying to push phosphorus ions this way. That means the acceptor ion should actually be pulled in that direction. So we should have the opposite effect, and we do see a little bit of that, okay. But that doesn't explain why this should happen, and also overall it should be isotropic. Why is it happening only in this region in this manner? So again, the explanation turns out that the self interstitials that are released during the diffusion process in the emitter, they end up coming far away in this direction around this, and wherever they are able to reach, they end up hastening the diffusion of the dopants in that region. So that makes the base dopants which are directly underneath the emitter and close to the emitter, them to diffuse fast, and outside you don't have the interstitials, okay. So that's one reason, that is the reason why this is happening. So we have to take care of this and design it appropriately. So what are the ways you can get around it? One of the things that we also notice is in arsenic, actually you find the counter effect of the emitter field, right? You find a dip in the base profile, you do observe that. Base doping actually goes down a little bit. That's good in some ways, but also not good in some ways, because you may have the base width changing with bias. So you don't want that. So as diffusion is very small, also arsenic diffusion is very small interstitial C component. So no emitter push effect is seen here. Okay, so you find in arsenic, you don't find it. It's a bulkier atom, and you don't find it has very small interstitial C component. So it's not playing that much of a role. Antimony, on the other hand, is substitutional in character. So there is no emitter push effect at all that is noticed in this. So this is one of the ways you can actually go for another dopant atom. In this case, it's available, so you can actually try to use those to overcome this emitter push effect. Of course, today with MOSFETs, this may not be that big of an issue, but there are lots of devices still made with BJTs for high-speed communications and all. So you might have to keep this in track. Now we come to the part of anomalous diffusion, which is corresponding to oxidation. So let's look at it a little carefully. Silicon and oxygen, they interact to form SiO2, it forms dislocations and strain. That's first thing. So that can end up changing the way things diffuse. Now what happens is silicon, and say there is a vacancy of silicon, that is very much attractive for the oxygen to form SiO. This is one reason porous silicon oxidizes fast, right? So what it does is it gobbles up any vacancy that is present. So that's one thing you notice. On the other hand, silicon and silicon, when there is, supposing there is the oxygen will come and displace this silicon. So that silicon becomes an interstitial. So wherever oxidation takes place, it is known that there is a lot of interstitials that are released into the silicon matrix, self-interstitial, silicon interstitials in silicon. They are released whenever you have oxidation. So now this should affect the way in which diffusion takes place. That's understood also, and people have worked on it. But there was a curious situation. So let's see what it is. There was a curious case of oxygen enhanced diffusion and oxygen retarded diffusion. So you find that in the case of boron, gallium, indium, aluminium, phosphorus and arsenic, whenever you are supposing you had silicon, you prevented oxidation in these places, you allowed only oxidation here. So wherever oxidation took place directly under it, because of the interstitials release, as the theory said, so you had higher diffusion. But on the other hand, when you have antimony, it actually goes the other way. How could you explain this? So the curious case of oxygen enhanced diffusion and oxygen retarded diffusion. So let's see what it is. So actually this can be explained in the following way. We can model for each of these the diffusion under the conditions of oxidation would be, there may be a constant element, but plus this. So what is it? Di times I over I naught, concentration of interstitials to the intrinsic concentration of interstitials, and similarly dV times concentration of vacancy divided by intrinsic concentration of vacancies. Now it could be modeled this way. It turns out that interstitial and vacancies are linked, right? Interstitial and vacancy, when they come together, they annihilate each other. It's similar to electrons and holes, right? So you have law of mass action, so you can write it in this manner. So that being the case, you can write this whole equation in terms of concentration of I and I naught. So V over V naught gets replaced by I naught over I. So you have a quadratic equation of diox in terms of concentration of I. Combining these two, you can actually plot this, and for the different materials you can actually plot it according to the values of the di and dv, right? So diox in the y-axis, this is d naught, this is the intrinsic value, okay? That will be the background thing. Actually, maybe one should add here thing. So you will have d naught here. Now because of this I and V varying, you will have a parabolic relationship. So you find that it goes through this. Now when does it become enhanced and when does it become retarded? That is a question, and that's what led to this whole thing. So it turns out that if I is lying between this, okay, you will find that you are in the diffusion retarded zone, and that's precisely what is happening in the case of antimony. On the other hand, if I was here or here, concentration of I, if it is here, it is value you will get will be well above d naught. So that being the case, it will be oxygen enhanced diffusion. So you are able to explain what it is. So what this is trying to tell you is, by using the physics and mathematics and understanding of our of thermodynamics and all this, we are able to explain a lot of these things which seem otherwise anomalous and meaningless, right? How can this happen? It's supposed to happen that way, but actually if you look at it carefully, you are able to explain all this, and that's what this is indicating. Now we come to another important aspect regarding dopant redistribution with oxide diffusion rate. I have tried to plot it in this chart. This column would be diffusion where the diffusion of the impurity in the oxide is slow. Within the oxide, it diffuses, that impurity diffuses slow, and within the oxide, this impurity diffuses very fast. Okay, these are two columns. Similarly, you can have two rows. Here we have the segregation coefficient. You might remember in the context of our silicon ingot growth. Here it's in the context of oxidation, and we also touched upon it when we talked about oxidation. the impurity that is present in silicon and the impurity that is present in the oxide. How do they segregate, right? So it turns, if the segregation coefficient M is equal to equilibrium concentration impurity at the interface in silicon, impurity concentration impurity in SiO2. This is what it would be. So now and diffusivity of the impurity in oxide also we are considering, and the rate of SiO2 intervention also has to be considered. So let's look at it. So in this particular case, boron diffuses very slowly in the oxide. Once it is in the oxide, it diffuses very slowly. But the segregation coefficient is less than 1. We have seen this also when we discussed about oxidation. So what it means is, at the surface this will dip down, but once it reaches silicon dioxide, it is not able to diffuse that fast. So diffusivity of impurity in oxide, if you look at it, it's slow. And also, as it is oxide is growing, this thing is moving in this direction. So you can actually model this in appropriate way, and you find that at the surface, because of oxidation, the p-type doping will actually go down. This is important, especially in MOSFETs. We talked about it when we talked about oxidation also, because the threshold voltage and other parameters can get affected. On the other hand, if the same oxidation was done with hydrogen in the background, and you had this boron segregation happening, it turns out in the oxide, boron can then diffuse very fast. It diffuses very fast. And what is its repercussion? We know that the segregation is in the direction of oxide. More will be going into the oxide, and there will be a dip in the concentration. But the fact that it is getting removed very quickly from the oxide means that at the surface the boron concentration becomes much lower. This is something to watch out for. It will be very different. The threshold voltage as per this calculation and this calculation will be very different. For example, if we are talking about the region under the channel where the gate oxide is grown. Okay, so you have to watch out about this. Now phosphorus, as we have seen, it piles up. We have already seen this. Now it does pile up, and here if this is not being removed very fast, the pile up will of course be more, right? Because the ratio of this to this has to be maintained. On the other hand, if you use gallium, what do you find? Everything goes away once it reaches oxide. So it doesn't pile up, it actually comes all the way down. Note that the very fact that the oxide is growing this way, there is a natural ploughing effect, right? The dopants that are there are going to remain there, but segregation coefficient ensures what goes where. But this tells us that you can have pile up of dopants in the case where M is less than 1 and oxide is not able to remove it fast. On all the other cases, you find there is a dip in the concentration. And in fact, knowing and understanding this helps you model these things very well. So let's take a quick look at the takeaways on this anomalous effect. Some concepts are there, so I'll just try to reiterate some of them. While canonical form of diffusion helps visualization of what is happening, it often needs a relook. This is a reality, and this is true with any level, any area of learning. There is no finality, right? You have to constantly be on the lookout to be clear about the current situation, current problem that one is tackling. The built-in field due to the dopant profile aids in the diffusion. Okay, this is something interesting. The electric field effect is such that there is a built-in field created, and the built-in field will facilitate the doping. So it will make the doping go faster and the diffusion go faster, so that the doping happens in a deeper region. So it allows the diffusion to go faster. Interstitials released can affect final diffusion profile. This we have seen in a few cases, but clearly interstitials can affect what is interstitial C-type diffusion can be facilitated. It enhances diffusion of concentration in the tail of a phosphorus, and also the emitter push effect, we found that it can play a role. The final diffusion coefficient is dependent on various other parameters, okay, because it is not just the standard canonical thing that we studied. There are various scenarios that may come up in the new device, in the new condition that you are fabricating, especially vacancies, interstitials, the charge states. Enhancement and reduction in diffusion rate also depends on the specific species and environment in which you do. If you have hydrogen environment, watch out. You may facilitate some other diffusion, you may change the doping profile. Oxidation modifies the doping profile of silicon under the oxide, and this is well known. We talked about it when we discussed about oxidation as well. Dependence of Si-SiO2 segregation plays a role. Also, how it diffuses in the oxide also plays a role. Okay, in the case of gallium, we found it still went down. We need to watch out. The essential takeaway, I would say, all the others are information and details, and you have to constantly learn them. But the key wisdom part is need to watch out for various new processes and how they affect silicon. To give an example, if you are silicidation, when you do, you are again releasing a lot of interstitials. You are consuming silicon, releasing a lot of interstitials. They end up affecting the doping profile in the, especially for smaller devices, it affects them very severely. Again, epitaxy growth, very common nowadays. When you do epitaxy, remember, it can affect the neighboring environment. Okay. So now let me conclude about the overall topic of diffusion. The key things are, diffusion is a fundamental process. There is no getting away from it. It is a question of knowing what it is, use it whenever possible, protect yourself whenever possible. VLSI Industries tries to make use of it where possible and make sure it understands the effects of diffusion so that it can protect itself. Mathematical models are really well developed, and it's fascinating to see how much creative and sophisticated all these investigations have been, and they continue to develop, and they are able to explain many of the phenomena reasonably accurately. Thermal budget is a very important concept that we talked about to plan the whole process. This is probably a very key takeaway, that if you do something what will affect you later, you should be careful. So, a very high thermal processes, you try to build it in the very early stages. If you want to denude the silicon, for example, which you anneal at a very high temperature in nitrogen ambient or something, you don't do it when you have built all the devices. You do it when no devices are built. So, none of the later processes are affected by that, and the thermal budget remain intact. You don't use it up. Orthogonalize the different diffusion process, and that's what we try and do. If we are not able to orthogonize, we create a new process and call that to be the thing. So, we have to work it out how it can be done. We need to be vigilant of the various anomalies in our model, and this is true about anything in science and technology. What we talk about are models of how we understand it. Models are at best a caricature of the reality. That being the case, it's a good idea to always keep reevaluating and confirming that what we are seeing, and even a simple experiment confirming what is a well-known theory of idea is worth a lot more than a lot of theory just assuming and going forward. It's a good idea to always check. Okay, so with that, we'll conclude our discussion on diffusion as a unit process for this course. Thank you.